All right, let's talk about the biggest question there is. How does it all end? I don't mean us or our planet, I mean everything, the whole show. Let's take a look at the ultimate fate of the cosmos.
You know, it's a thought that kind of pushes science to its absolute edge. We're pretty sure the universe had this fiery, incredible beginning, so logic, physics, it all tells us there has to be an end, right? But what in the world would that even look like?
Well, it turns out the answer is hiding in the fundamental forces that have been sculpting our universe for billions and billions of years. To find it, we've got to go on a journey into deep, deep time with the laws of physics as our only guide.
Okay, so science has basically put three big ideas on the table. First, there's the big crunch, the idea that gravity eventually wins, pulling everything back into one massive crunch. But that's looking really unlikely because the universe is actually expanding faster than ever. Then there's the big rip, where that expansion gets so crazy it literally tears atoms apart. That one requires a kind of energy we've never actually seen. So that leaves us with the front runner, the one that best fits the evidence we have. It's driven by that mysterious dark energy, and it's called the heat death, or the big freeze, a long, slow fade to black.
So what's the engine behind this slow, inevitable decay? You might think it's some super complicated, mind-bending theory, but it's not. It's actually a single, really simple rule. A rule that applies to your morning coffee just as much as it applies to galaxies. It's one of the most bedrock laws in all of physics.
Seriously, this coffee analogy is perfect. All that concentrated energy, that heat, that order, it always spreads out. It wants to become uniform and, well, kind of boring. Your hot coffee is this little island of order, but it can't help but share its heat with the colder room until everything is the same lukewarm temperature. Now, just scale that up. The universe is the biggest coffee cup you can imagine, and it's doing the exact same thing.
And there's a name for this unstoppable slide into disorder: entropy. You can think of it as the universe's one-way street. The second law of thermodynamics is relentless about it. Things fall apart, they don't just spontaneously organize themselves. In fact, this is the very reason time seems to move forward. Time is basically just the measure of entropy's constant, unstoppable increase.
Think about a star. It's this beautiful, magnificent pocket of low entropy. It's concentrated energy doing useful work, right? It's making light and heat. But all that energy is constantly radiating away, spreading out into the empty void. It becomes useless, high-entropy waste heat. The entire story of our universe, from the Big Bang to the far, far future, is this one-way journey from low entropy to high entropy.
So, let's start our trip down this cosmic timeline. We'll begin in the only era we've ever known, the age of starlight.
You can really break down the entire future of everything into four great epochs. We're right here, at the very, very beginning, in what's called the Stelliferous era, the age of stars. After this comes the degenerate era, the age of stellar corpses. Then, the almost unbelievably long black hole era. And finally, the dark era. Our bright, busy, star-filled cosmos, it's just the first chapter in a very, very long book. And it's by far the shortest.
The end of our bright era is going to be this slow, majestic twilight. Our own sun will swell up into a red giant in about 5 billion years. Across the cosmos, the huge clouds of gas that act as stellar nurseries will just run out of fuel. The lights will go out one by one until only the faint, super long-lived red dwarf stars are left burning. And when the very last one of them finally flickers out, the universe will go dark for the first time in its history.
100 trillion years. Let that sink in. That's more than 7,000 times the entire current age of the universe. By that point, every single star will be gone. The cosmos will officially enter a new and profoundly darker age.
Okay, so once that last star is dead, the universe will be filled with nothing but their ghosts: white dwarfs, neutron stars, and black holes. And it's here, in this total darkness, that things get really, really weird. The very fabric of matter itself starts to come undone.
So it turns out that even those stellar corpses aren't forever. Physics actually predicts that protons themselves, the building blocks of every atom, are fundamentally unstable. Now, the process is impossibly slow, but over these vast eons, every single proton is expected to just decay. That means all the matter we know and love will literally dissolve, leaving behind nothing but a thin soup of radiation and the last holdouts of gravity, the black holes.
10 to the power of 40 years. It's a number so big that trying to write it out is basically pointless. Our brains just can't comprehend it. That's the timescale we're talking about for all the matter in the universe to just dissolve. After that, the only things left that you could even call objects will be black holes.
But get this, even black holes, the very symbol of permanence, aren't forever. Stephen Hawking figured out that thanks to some bizarre quantum effects right at their edge, they leak. Yep, they leak. It's a process we now call Hawking radiation, where they slowly, particle by tiny particle, evaporate back into nothingness.
And they don't go out with the whimper. After these incredible eons of slowly evaporating, a black hole's end is a sudden, spectacular flash of high-energy gamma rays. These will be the last fireworks, the last significant events to happen in the entire history of the cosmos.
That's a googol, a 1 followed by 100 zeros. It's a number that just completely defies human comprehension. But that's how long it will take for the biggest, most massive black holes to finally evaporate. And once that last one is gone, the universe enters its final, ultimate state. So, we've arrived, the end of time, the dark era. The universe has finally reached maximum entropy, the state we call heat death. But even here, right at the end of absolutely everything, physics might have one last, shocking twist up its sleeve.
This is it, the big freeze, a universe where entropy has completely won. Energy is spread so perfectly thin and so evenly that nothing can ever happen again. No work can be done, no new structures can ever form. It's a state of perfect, eternal, and absolute stillness.
Eternal stillness. I mean, that sounds pretty final, doesn't it? But the weird, counterintuitive laws of quantum physics, they might not allow for such a simple, neat ending. The slow fade to nothing might not be the only game in town.
There are two wild cards left in the deck. The first is a sudden, shocking end. It's called vacuum decay. The theory goes that our entire universe might be living in a false, unstable vacuum state. At any second, a bubble of a more stable reality could pop into existence, expand at the speed of light, and just erase everything as it rewrites the fundamental laws of physics. Then there's the other option, a new beginning. Given an infinite amount of time, a random quantum fluctuation could, against all imaginable odds, spontaneously create the conditions for a new Big Bang, starting the whole cosmic cycle all over again.
And that really is the ultimate question, isn't it? Is our destiny a slow, silent, inevitable fade into an empty void, thanks to the relentless march of entropy? Or do the strange, wild rules of the quantum world leave the door open for a sudden, violent reset button? We just don't have the answer. But it sure seems like the universe's final chapter is a long, long way from being written.